In this video, we're going to look at calculating percent compositions, empirical formulas, and molecular formulas. The first question reads, what is the percentage of aluminum in the mineral bauxite, aluminum hydroxide? Our first step is to figure out the empirical formula of aluminum hydroxide. We know that aluminum has a charge of +3 and the hydroxide polyatomic ion a charge of -1. That means that aluminum will bind with 3 hydroxide ions to form AlOH3, or bauxite. To calculate percent composition, we're interested in the mass of our element of interest over the total molar mass. In this case, aluminum has a molar mass of 26.96 grams per mole, and our total molar mass for bauxite, 78.01. Multiply that by 100 to get it back into percent form, and we find that aluminum is 34.59%. The second question asks, a given compound has 2.2 grams sulfur and 7.81 grams of fluorine. What is its empirical formula? A reminder that the empirical formula is just the ratio of sulfur atoms to fluorine atoms in this compound. It's not necessarily the actual molecular formula of a given molecule. So, to start this problem, we want to take the masses of each for sulfur and for fluorine, and we want to divide those by their molar masses. For sulfur, each mole of sulfur has a mass of 32.07 grams, and each fluorine has a mass of 19 grams. This is converting the mass ratios to now mole ratios. At this point, we then want to simplify the ratio. The best way to do this is to divide by the smallest number. This is not going to change the ratio, it's just going to simplify it. 5.99 is awfully close to 6. So what we find here is we have 1 sulfur for every 6 fluorines. These are both non-metal compounds, so we know this is a covalent compound, and we could name this sulfur hexafluoride. Question 2 asks to find an empirical formula for a compound that's 61% tin and 39% fluorine. This will be slightly different in that we're given percentages to start with. Here, you want to assume that you have 100 grams of the compound. 61% of 100 grams is 61 grams, and 39% of 100 grams is 39 grams. Just like before, we want to convert our gram ratios to mole ratios. Tin has a molar mass of 118.7 grams, and fluorine still has a molar mass of 19 grams. Converting our mass ratios to mole ratios, we find that there's 0.514 moles of tin for every 2.05 moles of fluorine. Just as before, divide by the smallest number. That will simplify the ratio without changing it. And 3.99 is awfully close to 4. So that tells us here we have tin combining with 4 fluorines. Tin is a metal, fluorine is a nonmetal. We know this is an ionic compound, so we could name this accordingly as tin 4 fluoride. The last twist on this is now finding a molecular formula. Unlike before, where we were simply finding the ratio of one element to another, with the molecular formula, we want to actually determine the specific formula for the molecule in question. Here we're given percentages of mercury, chlorine, and oxygen. Just as before, we want to take our percentages and assume that we have 100 grams of the compound. That will allow us to convert our percentages into masses. 70.6 grams of mercury, 12.5 grams of chlorine, and 16.9 grams of oxygen. Just as before, put these over 1 and multiply by their molar mass. Mercury has a molar mass of 200.6 grams. Chlorine has a molar mass of 35.9 and oxygen has a molar mass of 16 grams. Converting our mass ratio to a mole ratio, we get the following ratio. Just as before, divide by the smallest number. That'll give us 2 very close to 1, 1 very close to 3. So what we have here for an empirical formula is HgClO3. That's our empirical formula. That compound has a molar mass of 254.05 grams per mole. From the problem, we had the additional information that the molecular formula was equal to 568 grams. What we can do at this point is take that molecular formula, the 568 grams per mole, and divide it by the empirical formula, and find that that equals 2. What that tells us is the molecular formula is twice as large as the empirical formula. Molecular formula or molecular formula equals Hg2Cl2O6. The only mistake in the problem here is a molecular formula would need to be calculated for a molecule. Ionic compounds, remember, combine in ratios and will only have empirical formulas. And our issue is we have an Hg ion and 2 ClO3 polyatomic ions. So really it's not a great problem in that you're calculating molecular formula for something that is clearly an ionic compound. The process is good. The actual question I gave you is a little bit of a misnomer. Thank you for watching. And again, we're looking at ways to calculate percent compositions, empirical formulas, and now molecular formulas.